Okay, so where we left off in the last video, we now are going to distribute. We have 2x cubed plus 6x minus x squared minus 3 minus 2x cubed plus 2x squared minus 2x all over x squared plus 3 squared. That gives you dy over dx is equal to x squared plus 4x minus 3 all over x squared plus 3 squared. We can leave our answer like this. Now we're going to go into a few more questions that may appear on your part 2 test. It's a little bit more of application questions. I'm going to do one with you and one you will do on your own. So we're determining the derivative at each given value of x. Now this one is a simple function, so I'm going to provide the answer. So when you get your derivative function, you should have dy over dx is equal to 13 over x plus 5 squared. Now, when you plug in the value of -3, the way we write that, dy over dx at x is equal to -3 should give you positive 13 over 4. I'm going to allow you to try that on your own to make sure that you are getting that answer. And let's do an example together. So we're going to have a cubic function in the numerator and a quadratic function in the denominator, and we're going to solve when x is equal to positive 1. So let's start dy over dx is going to be equal to the derivative of the first function, the top function, 3x squared, times my original bottom function, x squared plus 9, minus the derivative of the top. And I can't reinforce how much you have to make sure that your quotient rule questions are difference. You have that subtraction sign as opposed to the product rule, which is a sum. Times my original numerator all over my denominator squared. Okay, now you would think maybe you would have to do the distributive property, but because we're dealing with more complex polynomials, I'm going to go ahead and substitute x is equal to 1 straight in without simplifying, just to show you that that is a strategy you can use. And we have to see these substitution steps. If we don't see these steps, you will be losing out on marks. So I do not want to see simplified calculations. We have to see how you got your calculation. So 3 times 1 squared instead of 3 times x squared. And instead of x squared times 9, 1 squared plus 9. Notice how I'm using the large square brackets here. Minus 2x, 2 times 1, with my x cubed in square brackets. Always clarify with me if you don't understand how and why I use the square brackets. 1 squared plus 9 squared. So that's going to give me 30 minus 2 over 100, which would be 28 over 50, which we can simplify to 7 over 25. Very straightforward. And let's go on to some word problem applications. Find the points at which the tangent to the curve is horizontal. Now, in order to be able to solve this, you have to know that the tangent would have to have a slope of 0 in order for the tangent to the curve to be horizontal. And once we set the slope equal to 0, we can solve for the specific points of x. I'm going to actually do both of these. So I have y prime is equal to the derivative of the top, 4x, times my original bottom function, x minus 4, minus 1, that's the derivative of the bottom, times my original top function, all over the bottom function squared. Repeating the rule over and over again to make sure that I don't make any mistakes, since it is a complex rule to remember and very simple or very easy to mix things up. So y prime, or you can do dy over dx, same thing, 4x squared minus 16x minus 2x squared over x minus 4 squared. Now, if we factor the greatest common factor, which is 2, oh wait, sorry, no, we can simplify this to 2x squared minus 16x over x minus 4 squared. But notice something. Because it says at which the tangent to the curve is horizontal, I can set this entire equation equal to 0 because the slope has to be equal to 0 for it to be horizontal, and set that equal to 2x squared minus 16x over x minus 4 squared. Now, when you do that, with cross multiplying, and you should all be very familiar with this, the 0 will cancel out x minus 4 squared, the denominator, completely. So I'm left with 0 is equal to 2x squared minus 16x, which we can then factor to 0 is equal to 2x times x minus 8. Now, this is the information I'm going to use in order to solve for my point. So I'm going to take the 2x for the first point and x minus 8 for the second point. So 2x is equal to 0 means that x is equal to 0. And setting x minus 8 equal to 0, that means x is equal to positive 8. So I should have said 2x is equal to 0 there. Now, to get the corresponding y is going to be my original function. You're substituting 0 into the original function. Sorry, let me move this up a little bit. So y is going to be equal to 2 times 0 squared all over 0 minus 4. That's my original function. That gives me a y value of 0. When I do the same thing with x is equal to 8, y is equal to 2 times 8 squared over 8 minus 4. That means that y is going to be equal to 32 So the solution to this question, the points at which the tangent to the curve is horizontal, are going to be at 2 points. This phenomenon is going to happen is when x is equal to 0, y is equal to 0, and when x is equal to 8, y is equal to 32. That's where you're going to see horizontal tangent lines. Now, for the next question, we could substitute and simplify the function first. So we can factor the top, factor in the bottom, and eliminate. So I'm going to do 2 methods. Method 1. If I factor my function, over x minus 1 times x plus 2, you'll notice I can cancel these x minus 1. So I'm left with x plus 1 over x plus 2. And I have the x restrictions. X cannot be equal to -2 and +1. At -2, we actually have a vertical asymptote. And at +1, we're going to have a hole in the graph. That's because we're eliminating from both the numerator and the denominator. So that's one particular method to solve. I'm actually going to focus on the methods we've been using all along, which is just using the derivative. So this time I'm going to use dy over dx is going to be my derivative of my top function, 2x, times the original bottom function, minus the derivative of the bottom, times the original top function. Now I'm going to leave this to you to actually simplify, distribute, and I'm going to jump ahead to the final answer, which is what I don't want you to do for the test, but I do want you to practice to make sure that you're able to get the answers on your own. When we simplify everything, you're going to be left with x squared minus 2x plus 1 over x squared plus x minus 2 squared. Now I want to factor this because unlike the questions we've had before, both numerator and denominator can be factored. So the numerator can actually be factored as x minus 1 squared. Now we have to be careful because x squared plus x minus 2 squared. So what we notice is when I can factor x squared plus x minus 2 as x minus 1 x plus 2, but we have to remember that both of them have the power of 2 here. Now x minus 1 squared can be canceled out of both. So my dy over dx is equal to 1 over x plus 2 squared. But you'll notice from method 1 that x, there was a vertical asymptote at x is equal to -2. And even when you graph this, if I try to set this function equal to 0, you'll notice that just like before, the denominator and the 0 cancel out. So I have a final answer of 0 is equal to 1, which means that for this particular question, there are no solutions. And this is particularly because there's a hole in the graph. when x is equal to 1. So there's going to be no point where there is a tangent to the curve that is horizontal. And you can graph this function to be able to visualize why this is the case. Okay, one final application question. The derivative is very straightforward in this particular case. So the first thing I'm going to do is find the point actually on the curve. So in order to find the point on the curve, I'm going to substitute or find y of 2. So plugging in 2 into my original function, 2 squared minus 1 over 3 times 2 gives me a value of 1/2. So my point is going to be when x is equal to 2, y is equal to 1/2. Now, in order to find the slope of the tangent, I need to find the derivative. So dy over dx is going to be equal to the derivative of the top 2x times the original bottom function minus the derivative of the bottom function times my original top function, all over the bottom function squared. So dy over dx is equal to 6x squared minus 3x squared plus 3 over 9x squared. When we simplify that and get rid of the common denominator, I have dy over dx is equal to x squared plus 1 over 3x squared. Now, in order to calculate the slope, I need to find the derivative slope of the function at x is equal to 2. So that's going to involve substituting 2 squared plus 1 over 3 times 2 squared, which is going to give me a slope of 5 over 12. So finally, to find the equation of the tangent line, equation of the tangent line, I need to use all of the information that I've collected and substitute it into y is equal to mx plus b. So I'm going to substitute my point, and I'm going to substitute my slope in order to solve for b. So 1/2 is going to be equal to my slope of 5 over 12 times my x value of positive 2 plus b. So 1/2 is equal to 5 over 6 plus b. We change that into a common denominator to solve. So b is equal to negative 1/3. That means my equation of my tangent line is going to be y is equal to 5 over 12x minus 1/3. And that concludes part 2 of our lesson today.